Now I know we've done word problems before, just a couple of sections ago, so you might feel a little cheated that we're talking about word problems again. But we've learned some things about quadratic functions since then, and those things are really important things. In particular, we've learned what the graphs of quadratics look like. They have a key point where the graph has either a highest or a lowest value. That key point's called the vertex. And that's going to be related to a lot of practical questions that otherwise you might not know that they can even be answered. So here's an example. This homeowner is trying to make one of these little rectangular dog runs for their dogs. In their garage or tool shed or something, they find that they've got 60 feet of fencing available. And the smart way to use that fencing is to put it up against the side of the house so that of the four sides of the rectangle, one of the sides doesn't need to be fenced. You only have to fence the other three sides. So a little sort of top-down view of what this thing looks like is they've got a house, and then they're going to build out from the house a rectangle like this. So you're sort of looking down from a drone in their backyard. And so that means this green stuff adds up to 60 feet. Now, how are they going to apportion out those 60 feet? They might do the lazy thing and just go 20 feet and 20 feet and 20 feet and make a little square there. But that turns out not actually to be the most efficient use of the fencing. They can make a larger dog yard than that has more square feet for their puppies. So we're going to have to do a little bit more work to figure out the proper way to split up the 60 feet to make the fencing for this dog yard. So what we're going to do is I'm going to pick one of the three sides. I'm going to pick this one that sticks out from the house, and we're going to call that x, because we don't know what it's going to be yet. It's an unknown. And then we apply some logic to figure out the other green measurements here. Like, for example, if that's x, this one over here is also x, because it's a rectangle. It's got to look the same on the left and the right. And then this horizontal portion here, this is a little tricky, but the idea is you started out with 60 feet of fence. You put x on the left, you put x on the right, all the rest of it, 60 minus 2x, is going to go along horizontally there. So those are the three sides that need to be fenced. What we're trying to accomplish here is we want to get the largest possible area. So let's take a second and talk about area. This is fairly simple. We're talking about a rectangle, not some funny weird shape. It's a rectangle. The area of a rectangle is length times width. And in this particular formula here, we know what the length is and what the width is. Well, sort of. We've got them labeled at least. The length is 60 minus 2x, and the width is x. Simplify that a little bit by multiplying those two together, and you will recognize that what we're looking at here is a quadratic. We've got an x times an x. That's not typically how we would write this sort of thing. We would typically write it as negative 2x squared plus 60x. You know, good old descending order. You got to put your squared term first. And then let's think about that equation there. A equals negative 2x squared plus 60x. Would it be easier to understand what's going on there if I said y equals negative 2x squared plus 60x? That has a graph. There's a graph you could draw for how those two quantities are related to each other. And it's a parabola. The leading coefficient is negative, so it's a downward pointing parabola. So it's going to look something like that. That's an incredibly sloppy picture. I mean, I didn't plug in any points. I didn't find anything. The only thing that I did right in that graph is I drew the thing pointing down. But that's good enough for what we're trying to accomplish. Remember, there's a purpose here. We want to get the largest area, the biggest value for the area we can possibly get. I think it's common sense that that's going to happen right there at the vertex. So ultimately, what we've determined here is that the question really boils down to a question about what's the vertex of this thing. So now let's answer that question. What is this thing's vertex? So you could use the completing the square stuff we've recently learned. You can use the vertex shortcut we learned a few sections before that. I really don't care too much what technique you use to find the vertex here. I'm going to use the vertex shortcut because I'm kind of in a hurry. So remember, the vertex shortcut is negative b over 2a. So that's negative 6 over negative 4, which is 15. That's not what we thought it was going to be. We thought it was going to be 20, 20, 20 for the 3 pieces of the fencing. It's not. X, that first measurement there, is actually only 15 feet. So the largest area will be created by having X be 15, which means the dimensions of this dog run, they're going to be 15 feet by, okay, well, wait a second. If X is 15, then 2 times 15 is 30. 60 minus 30 is 30. This would not be an adequate answer. Remember, with word problems, you should always read them one more time at the end. The question here says, what is the largest area they can fence in, and what will the dimensions be? We've done the and part. This is what the dimensions will be, but we didn't answer the first part of the question. We have to say what the largest area is. Well, we kind of have a little shortcut here since we already did the second part first. Isn't area length times width? And don't we have the length and the width? So we could just very quickly get the area by going 15 times 30. That's 450 square feet. If we had built it the way we thought we were going to in the beginning, where we were going to go 20, 20, 20, the area would have been only 400 feet. So that's a significantly larger rectangle there. It has significantly more area. That's enough extra area to put in like one of those self-feeding water bowls and maybe a little dog house with a nice little mattress pad or something in there. You know, this is going to make for a nicer dog run for your pets than it would have otherwise been. Okay, that's one example of a type of a word problem that ends up giving you a vertex as the important part of it. I'm going to show you another one that's a little bit more technical and that's going to lead into a bigger idea. So this next word problem seems a lot more practical. This is a business. I mean, if you're building a dog run for your dogs, it's not really that important that you get it exactly right. But now we're talking about a business. This company called Superstorage, they build storage cabinets, and they've figured out that the average cost per cabinet follows this sort of a graph here. And let's talk briefly about what we expect that graph to look like before we even look at the equation. If you graph your average cost versus the number of things produced, something's going to happen with this graph here. For example, oops, dang it, sorry about that, back on track. If you go through all the process of designing the cabinets and hiring people and renting a factory and building all the machines and getting all the machines adjusted exactly right and getting all the tools and raw materials, and then you just build one cabinet and you go out of business, that's going to be a super expensive cabinet, like ridiculously expensive. What you really want to do is produce more and more cabinets so that those initial startup costs get spread out amongst many cabinets. So at the beginning, your graph may have a very high value, but it's going to drop. Now, it's never going to go negative, of course. It can't just, keep going down and go eventually negative cost per cabinet. That can't be realistic. It's going to have to level off. And in fact, realistically, there's this thing that happens where after you've produced a bunch of cabinets, now you don't have enough space. You've got to rent another warehouse. You got to start another factory. Your machines need to get repaired, so now you got to hire a repair person. So there's actually a point where it's no longer productive to make more and more, and the graph starts to go back up. So if you think about a real business in the real world, their average cost graph is going to look something like this. So now, when you actually look at the equation and you see that it's quadratic, you're not really too surprised. It's like, yeah, I kind of knew it was going to have to be quadratic. A straight line doesn't make sense here. But there is a place, of course, that you want to be on this graph. You want to be right there. If this is your business, if you work for Superstorage, you want to get the minimum average cost per cabinet down as low as you possibly can so that you can make profit off of selling these things. This is how this is how you pay your rent. This is how you feed your family. So this is worth it. So again, like the previous problem, it really boils down to the question about where's the vertex. And that's kind of the thing about these word problems in 11.8. They pretty much always turn out to be about the vertex. So now we have to talk about where's the vertex for this thing. And the vertex shortcut is still a really good idea. Negative b over 2a. So that would be 1.3 over 0.4. And you'll notice these more realistic problems, they a lot more often require you to grab a calculator. 1.3 divided by 0.4 is 3.25. And then you got to make sure you're actually answering the question. The question here says, what is the minimum cost per cabinet, and how many cabinets will they need to build to achieve that? X is which one? You got to stop and go back and reinterpret. X is the number of storage cabinets when they build X hundred storage cabinets. So when they say how many cabinets, that's what we just figured out. They're going to have to produce 3.25 hundred cabinets. Well, that's really awkward. Who would say 3.25 cabinets? 3.25 hundred, that's 325. So please don't say things awkwardly when in day-to-day life you would say something like 325. Say 325 cabinets. And then the other part of the question here is, what is the actual minimum cost going to be? So that's the y value. You've got to take 325 and plug it into the cost equation here. So x was 3.25. We plug in 3.25 just like you would normally do with any other x. And again, notice these realistic problems, you got to go grab a calculator. This is not something you're going to be able to work out in your head. End up with 1.29, and again that's C of x is in hundreds of dollars, so that's $1.29 $100 average cost per cabinet, so $129. So in the best possible setup, you can get your costs as low as $129 per cabinet that you sell, which means you better sell it for more than that. Maybe mark it up to $200 or something like that. But you're never going to be able to get your average cost below that unless you fundamentally change something about the business. Now there's one last kind of interesting thing going on here that we got to talk about, and that is, how did they get this equation? Where did this equation come from? I mean, we drew the picture sort of abstractly thinking in general terms, but look at those coefficients. Where did this equation come from? If this was your actual business, it's not like this is going to magically drop out of the sky and, ta-da, there's the equation. It's not like you can go down to City Hall and they've got all the equations for every possible business sitting there and some clerk will look it up for you. No, there has to be a way to produce this equation. And the equation like this, the way it gets produced is by experiments. People try building and they see what ends up happening. And that ends up giving us a process called curve fitting that we have to talk about. And in order to keep the process simple, I'm going to use extremely simple data, not like in the real world where it has all sorts of decimal places in it. Here the, quote, data is just going to be 3 points. You have an x value and it gives you a y value. And then you have a different x value and it gives you a different y value. You could think of these as experiments where somebody is picking a number for x and experimenting to see what y comes out to be. In the real world, those numbers are much messier, but the basic technique is the same technique. You're trying to get this all to fit into a quadratic function. That means you want to get a function that eventually is going to look like this. And what you know about this function is that when you plug in 1, y comes out to be 4. If you plug in 1, y comes out to be 4, that's actually an equation where you've plugged in for x, so x isn't in the equation anymore. You plugged in for y, so that's not in the equation anymore. But you still got a, b, and c that you don't know. And you do that with the other points as well. Plug in -1 for x, and y is supposed to come out to be 6. That's a different equation. And if you plug in -2 for x, y is supposed to come out to be 16. That's a third equation. Hey, wait a sec. 3 equations? 3 equations, and we have 3 unknowns, a, b, and c. Oh my gosh, it's a system of equations. Yep, that's right. Fitting data to make an equation ends up giving you a system of equations. Now think about it. If the equation hadn't been ax squared plus bx plus c, if there had been an x cubed term as well, so it had been ax cubed plus bx squared plus cx plus d, if there had been 4 parts to this, you would have needed 4 points. And if it had been a 5th degree polynomial, you would have needed 5 points, and so on. So the number of the degree you've got, you always need 1 more than that in the number of points. So a 2nd degree polynomial requires 3 points. A 3rd degree polynomial would require 4 points. A 5th degree would require 6 points. A 20 degree polynomial would require 21 points. But it will always lead to a system of equations. And then you solve the system of equations. So if you'd like to pause the video and then press play, see if you get the same thing. When you're all done, you should end up with this. Don't forget, just finding a, b, and c isn't the whole story. You're supposed to be writing it up as an equation.